So, welcome all of you. Before we get going, there are a few things I just want to lay out for all of you. So first of all, I like a very interactive audience. So if there's a question that occurs to you in the course of the conversation, in the course of the talk, ask it immediately. Because if you're wondering about it, there are other people in the room who are going to be wondering about it. So the second thing is, and this is part of being interactive with the audience, I also am going to ask you questions through the course of the talk. Now, most of these are going to just be raise your hand kind of questions to get a feel for what your experience is like so I can tailor what I say. But, like any good scientist, the very first thing we're going to do is calibrate. So, how many of you can raise your hands? That's actually a really good percentage, generally speaking. Excellent. Cool. So diving right in. How many of you remember the Colonial Pipeline hack? About, last year, May timeframe, expensive gas on the East Coast. So this was a cyber attack, and it turned out that as a result of this, the Biden administration issued a cybersecurity executive order, which was remarkably well written. I'm the kind of geek who reads executive orders recreationally over the course of decades, and it's really unusual to read one that touches on a technical matter that actually gets so much right. And one of the things that came up in that cybersecurity executive order was software bills of material, SBOMs. In other words, what is actually in the software you're running? Now, this was in May of 2021. Turns out none of this was actually terribly new. So how many folks have heard of SPDX? Okay, a few. So SPDX was an effort that launched in February of 2010, and their purpose in life was to try and produce a standard format for software bills of material. And they've cranked along nicely since then, to the point where they're now an ISO standard for expressing software bills of material. But this is where I found myself in 2008. So in the mid-2000s, a problem landed on my lap at Cisco, where we were shipping tens of thousands of software releases a year, and we needed to be able to know precisely what was in them, for a variety of reasons. The first reason was for open source license compliance. But our third-party security people rapidly realized that knowing what's in your software is the key to doing modern security. Now, of course, we realized this almost 15 years ago. And so I had built out, by 2008, a fully industrialized system that could capture, process, and make use of tens of thousands of SBOMs a year for both security and open source licensure. So I've seen a lot of this stuff. So as with anything else when you do it early, and this was certainly the case when I was building out SBOMs at an industrial scale at Cisco, mistakes were made. You're trying something for the first time, you don't actually understand all the wrong answers, so you try a bunch of things that look plausible. But the flip side of making mistakes early on is you learn a ton about the problem space. And so when the Colonial Pipeline hack came back around, a bunch of the friends that I had made in the broader SBOM community of the industry, from which I had previously long since moved on, came around again and said, look, the time is right. The iron is hot. It's probably time to roll out some of your crazier ideas from over the years. And so I gave this talk. Literally, if you look at the timeline, May 6th, the Colonial Pipeline hack happens. May 12th, the cybersecurity executive order lands. About 2 weeks later, I give this talk to the NTIA and a bunch of the folks getting together, describing what has become known as GitBOM, which is one of those crazier ideas, and we will go into great detail on here shortly. This sort of percolated in the background over the summer and the fall, until in February 2022, we publicly launched the GitBOM community. It went pretty well. As you can see, we had a huge amount of interest on Twitter. We had a lot of visitors to our site in the first few weeks. But the real story here is actually how you think about this process. So when I came back into the SBOM world, you sort of start and you look around and you try and figure out what's going on with supply chain security. And this is actually what it looks like the first time you look at it from the outside. And please note, I had a lot of experience in this area. This is still what it looks like. Now, this is not meant to disparage the really cool things that are happening. Because you do have really interesting things happening, like in Toto, that is collecting attestations from everyone along a chain of what they did in the process of producing your software. Or the SPDX process that it continued to mature, or some of the signing things that are going on. All of these are good things. But it's also kind of a lot. So this sort of brought me back to the fundamentals. So why do we actually care about supply chain security at all? It's a massive pain in the ass. But the real question we're trying to be able to answer is, am I safe? Now, over the years I've learned that simplicity is actually the key to solving any problem well. And the reason is because simple things are reliable. Simple things are performant. Simple things are secure, and simple things scale. Complexity tends to fail on all of those counts. And one of the other things that I had learned over the years is often you can make systems more complicated by just how you look at them. So, real simple example we can all sort of take back to our school days. If I've got a bunch of items along a line, I can specify all the items along that line with 2 coordinates, right? So the complexity of my system is 2 variables. But that's not actually what's going on here. If you tilt your head to one side a little bit, you can discover you're actually only dealing with one line. You're dealing with one variable. And so what we're going to talk about here today with GitBOM is a little bit of that head tilting towards a simpler way of looking at a corner of the world in the effort to make this all more tractable. And so we start by asking super simple questions, profoundly simple questions. The first one is identity. What is this software artifact? Maybe it's a container, maybe it's an executable, maybe it's a jar file that you're going to execute or load into a web server of some kind. Dependency. What's in this artifact? And when I talk about dependency, I really mean what went into it all the way back to the source code level. And then finally, metadata. What else do we know about this artifact? So drilling into the first question, identity. What is this software artifact? So we should probably first talk about what we mean by a software artifact. It's basically any software object of interest. It could be source code of any language, right? So a C file, an H file, a Java file, a Python file, a Go file, a Rust file. Any of those are software artifacts. It could also be further up the chain of production. Maybe it's object files that got compiled by somebody into an SDK where they're not giving you the source code files, they give you the object files. In my world doing embedded development, this happens all the time from chipset vendors. It's very common. It could be class files in Java, the result of compiling your Java to Java bytecode. It could be jar files that aggregate them together. It could be compiled Python code. It could be an executable of any sort on any of the systems you might be running on, Windows, Linux, Mac. It could be a deb or RPM package, or it could be a Docker image. All of these are software artifacts. And what they all have in common is they're all representable by an array of bytes. And that's the ultra simple commonality that we're going to start by pulling the thread on here. So the first observation we make is there's a lot of ways to talk about artifacts being equivalent, right? If I have 2 simple Python scripts and I change the variable name in one of them and not the other, in some sense, they're equivalent. They do the same work. But that kind of equivalency is very localized to the language and environment you're working in. And so in GitBOM, we adopted the world's simplest notion of equivalency. 2 artifacts are equivalent if and only if they have the same array of bytes. Very simple, turns out to work for every language. And it should therefore be possible to identify each artifact with a unique identifier. Now, the first question you might ask is, what would we like to be true about identifiers? Right? My first name is Ed. It's a terrible identifier. It's great for conversation. There are a lot of Eds in the world. So it turns out what we actually wanted identifiers for artifacts is we'd like them to be canonical. Independent parties who have exactly the same artifact should be able to derive the same ID. If I have a Docker container, you have the same Docker container, we should have the same ID. If I have an executable that was compiled from C and you have exactly the same bytes, we should have the same identifier. The second is uniqueness. Non-equivalent artifacts should have distinct IDs. That's back to the problem with Ed as an identifier. It's not unique. Many people are named Ed. And then the last thing you'd like it to be is immutable. You don't want it to be the case that identifiers change over time. If I've got a set of artifacts, I would like it to be true that if I change the artifact at all, I get a different identifier. So it turns out there's a large number of non-solutions to this problem that have been explored. I will mention a few of them. This is not an exhaustive list. Right? So the first one is file name. We all use file names every day. They're a fantastic way to find things. They locate things in your file system. But they actually don't tell you anything about the identity of the thing. They are non-canonical. Right? I may name the file foo.c with a path in my home directory, or someone else may name it as a path in their home directory. I can change the file under the same name, and it retains the same file name. It's not immutable. And it's also not unique. On different systems, I can have the same file name with entirely different contents. So lots of other people sort of extended the concept of locators with file names to look around and say, well, what if we used a URL? There's even an entire really excellent standard called Perl for package URLs, trying to sort of sort this out as well. But this has the same problems with not being canonical or unique or being immutable that you run into with file names. And then the last one you run into, which is very common in the SBOM world, is to say, look, minimum elements of an SBOM: the component name, the version, and the supplier. So how does this sound to most of you? Does this sound good, bad, indifferent? Have you seen this before? So it's got a few problems. So the first one you run into is that people may use different names for the same thing, right? So Cisco might call the package kernel. Microsoft might call the package Linux kernel. Totally different names, same thing. The second thing you run into, and this is subtle, is we may have different ways that we format the version. Cisco puts a V in front of the version. Microsoft doesn't. And then the second is the supplier. The supplier is an issue of provenance. It's who gave you the thing. But it doesn't actually tell you anything about what the thing is. And so this also, while very descriptive, doesn't provide a canonical, unique, and immutable identifier. And then the other problem you run into when you try and specify these things at the level of packages like the Linux kernel is if you go and build the Linux kernel, like let's say we can sort out all the rest of the things, and I build Linux kernel version 5.17.3, there's about 50,000 source code files on the Linux kernel. Typically, if you build the Linux kernel without much configuration, maybe you've built about 3,000 of them. Which 3,000? That's a pertinent question when you're trying to figure out whether or not you have a vulnerability. It's not a question you can answer with this sort of an identifier. So it makes us sad. Questions so far? All right, we'll keep going. So the good news with an identity is this is already completely solved by Git, right? Git has already solved the problem of identity for arrays of bytes for source code files. So Git computes an object ID for the contents of every file that it stores in a Git repository, takes the contents, not the file name, not the location, the actual array of bytes, kicks out a 20-byte hash, and most of the source code files that you care about in the world today are already being indexed by Git in a repository somewhere. So we've already indexed the vast majority of the most interesting artifacts in the system. So Git is a little deceptive. Git's not actually a source code management system. How many of you thought Git was a source code management system? It's not really. It's an object store or a Merkle tree masquerading as a source code management system. Because it turns out these are both very useful things for doing that. Now, a Merkle tree is very simple. It's a tree where every leaf node is labeled with the cryptographic hash of its data block. So every file has an ID. And every non-leaf node, everything that relates things together in something like a directory tree, is labeled with the cryptographic hashes of the labels of its child nodes. This is why in Git, if I give you a commit ID, I can't forge to you which files were in that commit. Those are set in stone. I can't change that because of the Merkle tree nature of Git. So, I believe in recycling. How do other folks feel about recycling? So when there are good ideas, I try not to reinvent the wheel. I try and borrow them. So GitBOM basically looks at Gitoids, the Git object ID, and says, why don't we use this for all artifacts, not just source code files? Which brings us around to dependencies. So if I build a thing, like I build an executable out of C files, right? I have a bunch of CNH files, I build them into a .o file. I have a bunch of .o files, I build them together into an executable. We call the tree or the graph, the directed acyclic graph of this, the artifact dependency graph. And it literally tells you everything that went in all the way down the line. So it turns out when you start thinking about this, you realize that it's not just for static things that live on just like the executable. You can also do this for running executables, where you can have your graph contain not only the executable and all the stuff that went into it, but any shared objects that you link dynamically at runtime and all the things that went into them. And of course, this also works for Java, Java class files, it works for Go, it works for Python, it works for basically every language, it works for Rust, it works for every language that we've actually talked to folks about. It also works for packaging formats like RPMs and debs. It also works for container formats like OCI, Open Container Initiative. It gives you a single way of looking at the world that you can generalize. And you can say, what if all the things I'm looking at, I just think about as artifact trees, independent of the language involved, independent of the packaging scheme involved, independent of all the other sort of other things that make life complex. And then use the Git object IDs as the identifiers for each of those artifacts in the tree. Now this is super easy because on the bottom they're already being stored in Git. But it turns out you can compute easily the Git object ID of a thing without storing it in Git. It's literally a simple hash function. So very easy, but implemented literally thousands of times in the ecosystem already. And then the next logical question is, how do you represent the structure of the tree? If I've identified all the nodes in the tree, how do I identify the relationships? And GitBOM has a very simple answer. You have a very straightforward, simple document format that we all agree on that says, okay, if I'm something like artifact 2 that only has leaf artifacts as children, I'll just have new line terminated records that say blob space the Git object ID of artifact 4, blob space the Git object ID of artifact 5, and we'll put all of that in lexical order so we all get the same one every time, independently, and we'll call this the GitBOM doc for artifact 2. You can see something similar for artifact 3. Now, artifact 1's interesting because in artifact 1, and this is where we get into the Merkle treeness of it all, it contains artifact 2 and artifact 3. They were built into it, like the .o files coming up into an executable. And for that, you start the same way, blob space and the Git representation of the artifact. But then you also have space bomb space and the Git object ID of the GitBOM document for artifact 2. And this is what gives you this Merkle tree all the way down. Now that was kind of moving quickly through. Do folks have questions? Is this making sense to everyone so far? Fabulous. You know, you never quite know till you hash it out. So the last thing we look at from a simplicity point of view is metadata. What do you know about these things? So a colleague of mine, Jeff Shute, said an SBOM is a format for organizing metadata that describes the makeup of software artifacts. SBOMs are fabulously useful for description. In fact, SPDX has done a killer job of this so far, but they're describing a ton of information. They include information about human understandable names. They include information about who gave it to you. They include information about when it was built sometimes. There's a huge amount of metadata that they include, all of which is interesting and important, but it's complicated. And so GitBOM takes the attitude of saying, look, all we're doing is constructing the artifact dependency graph. And you can take any kind of metadata, whether it's an SBOM or anything else, and you can refer into that graph using the Git object IDs either for the artifacts in that graph or for the relationships. So you can use this for CVEs. You can use this for vex statements, talking about notification of whether you're vulnerable to something or not. You can use it in SBOMs, right? We've already got a place in SPDX where you can refer to the GitBOM tree from the SPDX SBOM. And of course, then this breaks down, if you're just thinking about GitBOMs and SBOMs, GitBOM just constructs the artifact tree, and you can use whatever SBOM-shaped thing makes you happy, plus you can store other kinds of metadata. Maybe you want to use something that involves in toto to capture cryptographic verification of who built it, or who tested it, or who deployed it. All of that can refer into the same tree by using the Git object IDs. So here's where life gets interesting. So if this is what is known about the world, how is it known? Right? This is where things get tricky. Can you trust this knowledge? So how many of you thought signatures when I was saying trust? We've all been, oh good, very few. We've all been conditioned to think about secure signatures in terms of trust and security. So signatures are fantastic, but all they really tell you is that somebody who had access to a private key produced the signature for a set of bytes. That's all you know. Now, we can choose to have that signify that it came from a trusted supplier that we believe is appropriately looking after their keys. We can choose to have this signify that somebody made an assertion about the world, but you don't know how they knew that. So signatures are of critical importance, but they're not actually really going to solve your problem. And now we get a little more philosophical. We root back a little bit into what is trust. So there's been a lot of thought about this. Dorothy Denning sort of really put a pin in it when it said, trust is not a property, but rather an assessment based on experience. It's a declaration made by an observer, not a property of the observed. Meaning, somebody is always making the assertion and they need to bring the receipts. Now, to put this much more simply, trust is always time dependent. In other words, it depends on when you're talking about. Maybe I trust this software today, but tomorrow we discover a very bad CVE with it, and we don't trust it anymore. It's asymmetrical, meaning that you trust me doesn't necessarily mean that I trust you. And it's contextual, right? It's within the context that you're trusting a thing. Which brings us around to build tools. Now, build tools are fascinating, things like compilers and linkers, because they transform their inputs, but in a way that makes it impossible to know intrinsically what went in. If I take CNH files, I can't really know from the resulting .o files everything that actually came out. In fact, if you talk to the folks who write debuggers, they have complicated heuristics to try and figure out when you're debugging if you're looking at the right source code. So you might say, okay, great, we'll scan the inputs. I've got a bunch of source code sitting out in my repo, I'll scan it. But it doesn't really explain the output because, as I pointed out with the Linux kernel example, not everything that's out there gets built at all. So you don't really know where it all went in the process. It's like giving you a list of ingredients and trying to get you to tell me whether the stuff in your pantry went into a pie that you baked. So post-hoc scanning, there's a huge industry of people who scan things after the fact. They'll scan your Docker container, they'll scan your executables, and they claim that they will tell you what's in them. Who here can tell me what kind of pie this is? Anyone? Might be. Could also be a peach pie. What if you're allergic to peaches? And what if your scanner determines that it's an apple pie? Because that's a really good guess. You've got a real problem. And I've been dealing with scanners for 15 years now, and they aren't even vaguely approaching the level of precision that you need to realistically approach this problem. So you come back again to what can you trust? Trust the build tools. Your compiler knows exactly what it compiled. Your linker knows exactly what it linked. Your Java class loader knows exactly what classes it loaded. The build tools have the right context at the right time for you to be able to find out the information that you need. And so what GitBOM fundamentally does is it advocates for building these compact artifact dependency graphs just out of the Git object IDs, embedding the get object ID of those GitBOM documents into the output artifact from a build tool and having the build tool do it because the build tool knows it. In a language neutral environment, language heterogeneous environment across all kinds of packaging formats with zero developer effort, involvement, or awareness. So quick question, let's see if we have any engineers in the room. How many of you are lazy? Now we know who the engineers are. Engineers are lazy. It's literally what we pay them for. So if you just keep layering more and more stuff on top of engineers that prevents them from getting from A to B, you got a problem. But if the act of building results in the construction of your GitBOM artifact dependency graph, now you got a chance. There is, by the way, here a QR code you can point your cameras at that will take you to GitBOM Dev, where there's a whole bunch more information. I will pause for a second to let folks point at that. So let's come back around to the original question. Am I safe? So take something like log4j. Turns out this literally comes from a single JDNI something.java file. You can trace this all the way back to the get object ID of that source code file. And if you have the artifact dependency graph constructed by GitBOM, you can trace out where that went, even if it's doing all kinds of crazy things that make it hard to find by simply cracking open your jar files. So really quickly, I'm going to take questions here in a second, but we have a vibrant community going. We actually have initial POC work with LLVM Clang and LLD, so we can actually build things, fulfilling some of this promise. That work will be upstreamed over time. We've got work being done in Go, Rust. We've got other tools that are actually looking at how to automate the process of extracting the source code hashes out of things that have CVEs by looking at the fix versus not the fix. That's things like BOM-SH. There's increasing interest from across multiple languages in this. We've had good conversations with folks in Java, JavaScript, OCI folks around containers, Golang. There's been a lot of enthusiasm for it. And we would love to see some of you come and join us. But even if you choose not to, hopefully one day you'll sort of look around and just realize this is happening because you build shit. Questions? We have a question up here.
However, you've got both of them somewhere down the line.
Right, so I think what you're asking is, if I get an artifact that it has an embedded GitBOM ID in it, how do I know somebody just didn't swap at a different GitBOM ID by, for ELF files, for example, we're putting them in a separate section, right? And the answer is, and by the way, for those of you who do architecture, what's the fundamental best lesson to learn as an architect? Make it someone else's problem. That's the very best trick as an architect. If any of you are starting or have ambitions towards architecture, that's the #1 trick. So we already have people signing artifacts. That exists in the world. There are whole projects like SigStore that are looking at making that better and smoother. We have no need to reinvent that wheel. But if I, as a vendor, give you a signed artifact that has an embedded GitBOM ID, you have an implicit assertion that I've actually given you the correct GitBOM ID from that artifact, because I signed it. And if somebody goes to change the GitBOM ID embedded in the artifact, you can tell, because the signatures don't match anymore. And so part of what GitBOM is doing is taking this very simple idea and putting it in a place where the entire ecosystem around it can benefit, but also can contribute to solving those problems. Did I answer your question? Awesome. It's a very good question. We have another question over here. Microphones are hard.
Hi, you mentioned something that said trust your build system. I don't trust build systems, right? Because they can be compromised.
Mm-hmm.
So I don't believe this addresses that. So I'm trying to figure out.
Right. So you're getting to the layers of trust, right? So can I trust my build system to have the proper context at the right time? Yes. Can I trust it to not be compromised? Not intrinsically, as you've pointed out. That said, because of the simplicity in GitBOM, we've been having a lot of conversations with folks who do enclaves
about looking at how we might do cryptographically verifiable build processes using just the scaffolding of GitBOM and then layering a bunch of other stuff on top of it. Because the kind of thing that lets you know it was this compiler that had these things built into it at this time and place, those are the kinds of metadata that you would want to capture from a cryptographically verifiable build process. And not having to solve that problem in a way that's just bespoke to this part of the problem is a huge advantage. So this incrementally enables us to get to more and more secure places. Did that answer your question?
Yes.
Awesome, because it's a very good question.
I do have one other question. You mentioned SPDX, obviously Git. Will this work with CycloneDX, and will it work with GitHub Enterprise, which is not github.com?
Right, so CycloneDX, we've already had the CycloneDX people come around and actually ask us what the URI format should be used for external identifiers, so should be fine. On the GitHub Enterprise side, at the guts under all the other goodness that GitHub gives you, what you will find at the very base is Git. So all the source code files that you're storing in GitHub Enterprise are still stored in Git. And that means that Git has still computed the Git object ID for all of them. So that's already still been indexed, even if you're using GitHub Enterprise. In fact, it turns out, even if you just happen to not be storing things in Git, we actually have someone in the community who, God help them, still uses Perforce. You can still use GitBOM, it's just your indexing is less fun because their source code is being stored in Perforce, and so that the hashes are different. Cool. Other questions? These have been fantastic questions. All right then. This is awesome. Oh, you got one more here?
Where in the pipeline does this work for something like higher level stuff like a WordPress or something else? Are you also expecting all of those kind of applications to provide their own GitBOM for those kind of stuff and not just like the lower level build tools?
Yeah, so what you're actually getting to is, and this is something we've had conversations with various communities about, there's always a little bit of difference by language and environment, right? And the GitBOM infrastructure is flexible enough that you could adapt to that. So for example, we've got the OpenJS people here, co-located with us. And I've talked to some folks in Node about how phenomenally useful it would be just to be able to, every time you require a package in Node, so it gets loaded, just log the current GitBOM status of that Node.js. Just log it. Just so you happen to know you have the GitBOM information logged, so that you can go back and figure out what happened. Because you do have dynamic environments like Node that loads things dynamically, Java loads things dynamically. And so that becomes useful and interesting. When you look at a thing like WordPress, the question you start asking is what makes sense there? Because WordPress, if I remember correctly, and please correct me if I don't, it's basically a bunch of Perl scripts that are being run, and then you get plugins that are bringing also a bunch of Perl. Am I remembering correctly on Perl?
PHP.
Oh, so PHP.
Of course, yeah.
Not enormously different, but a little bit. And it may be running in a runtime. Is Zend still building runtimes that pre-compile things, et cetera, et cetera? Apologies, it's been well over a decade since I played in PHP. And so you can start reasoning about the artifact tree of your running WordPress instance. You could even, if you can think about something useful to do with it, talk about the grafting in as a branch off of that some of your content. Not sure if that's useful, but it's mechanically doable. And so that kind of thing would be a really interesting conversation to have with folks who are working in PHP. Because I last used PHP in Angular almost 20 years ago. And so, as I said, you saw from my point of view, like, there are things that have obviously changed in that time. Did that help? Did that answer your question?
Yes. Slight follow-up then is the gitbom.dev like where I'd find all the community links and stuff to like start those kind of conversations?
Absolutely. Sorry, right here. I forgot to go to my last slide. So if you've got QR code scanning phones, this takes you straight to gitbom.dev/community. And we have weekly meetings that happen Tuesdays at 11 a.m. Pacific, which is 1 p.m. Central, where you're currently sitting. We have Slack channels, which we also have mailing lists. People tend to use the Slack channel more than the mailing list. There's a whole bunch of stuff. You can see the meeting minutes. You can get linkages to the videos that we have of all of our meetings, complete with indexes you can click on the timestamps for. So you can come up to speed pretty quickly, and we're very easy to engage with. Cool. So no questions from the folks in the back. That's okay. It's okay to be shy. All right, it's been super fun talking with you all. You've had excellent questions. You've been very engaged. All of you can raise your hands, which is an anomaly. And I'd be happy to talk to people in the hallway afterwards about GitBOM if you'd like to continue the conversation.